Hi everyone. This is the final lecture on the instrumentation amplifiers. So far we have discussed uh, the different performance metrics of instrumentation amplifiers, mainly CMRR and gain error, and how do they depend upon the op-amp gains that are used in the instrumentation amplifier. In this lecture, we will look at another very important specification, which is the bandwidth of a instrumentation amplifier. Okay, that tells you how fast the instrumentation amplifier can respond. So let's assume you apply a differential step input of magnitude say 0 to delta V. You would expect the output to rise to a final value of delta V times G, where G being the gain of the instrumentation amplifier, which G happens to be equal to G1 times G2, where G1 is the first stage gain and G2 is the second stage gain, the subtractor's gain. You would want it to settle within a certain time. Ideally, you want it to settle as fast as possible, which means it has to have as low time constants or has as wide a bandwidth as possible. Now, to analyze the frequency response, we will mainly focus on the differential frequency response, right? Common mode, anyways, it doesn't matter. The amplifier is supposed to reject all the common mode signals. It's only supposed to amplify the differential signals. Okay, so we'll only consider the differential response of the circuit. If you look at it differentially, an instrumentation amplifier is nothing but a cascade of the first stage is non-inverting amplifier. It's just a plain old non-inverting amplifier. Okay, it's not complicated. The second stage happens to be a subtractor. And if you guys recall from our previous lectures on the frequency response of op-amp based circuits, we already discussed in great detail the frequency response of non-inverting amplifiers and subtractors. So we just have to use those results and very quickly analyze, how the UGB of the op-amps will determine the UGB of the overall instrumentation amplifier. So since an instrumentation amplifier at its heart, right, it's just a two-stage amplifier. The first stage is a non-inverting amplifier. The second stage is a subtractor, right? It's just a two-stage amplifier. I can model it as, remember again, we said that the op-amp can be modeled as a single pole response. The op-amp's gain is given by A upon 1 plus S by omega P. And we said for all practical purposes at very high frequencies, this can be written as omega U by S, like a integrator. Okay, this is the op-amp's frequency response. Since there are two op-amps in the circuit, there are two stages in the circuit, I'm going to call the first stage as simply A1 of S. Okay, the first stage as A1 of S, the first stage frequency response as A1 of S, which is the frequency response of both the first stage op-amps. I'm going to call it as A1 of S, and their UGBs. The first stage UGB is omega U1, and the second stage op-amp, since I've used A3 as a notation for it, we will call omega U3 as the UGB of the second stage op-amps. Okay, the second stage op-amp. So I can write it this way. The closed loop response of the first stage can be expressed as G1 is the DC gain of the first stage, which is G1 is given by 1 plus 2 RF by R. And a pole. The pole is here the 3 dB bandwidth of the first stage. Omega 1 is the 3 dB bandwidth of the first stage. Okay, that is cascaded to another amplifier, that's the subtractor amplifier, and that again has its own frequency response given by G2 by 1 plus S by omega 2. Omega 2 is the 3 dB bandwidth of the second stage, which may depend upon omega U3 and so on. We'll see what is the dependence and all that. Now, whenever you cascade two amplifiers, right, whenever you cascade two transfer functions or two amplifiers with a single pole response, the overall speed of the system is determined by the slowest of the two systems. Okay, that is telling in terms of time domain. Whenever you cascade two systems, the UGB, the overall bandwidth of the cascaded system, will be lower than the lowest bandwidth of the two systems. So I can write let omega 3 dB be the 3 dB bandwidth of the overall cascaded system, that will be lower than minimum of omega 1 and omega 2. So that's what I mean by that. This is a frequency domain way of saying the 3 dB bandwidth of a cascaded system will be lower than the minimum of omega 1 and omega 2. So this here is minimum. Okay, so which means the slowest of the two systems, which means the system which has a lower UGB, will dictate the overall response of the system. So all we need to do is find out what does this omega 1 and omega 2 depend upon, and based on that we will take a call who will dictate the overall response. And I mean, how does the circuit designer who designs these instrumentation amplifiers, okay, how does his design specifications for these op amps come from? Where do they come from? Okay, that's what we are going to look at. So as I started the discussion, I said that when I started the discussion, I said the first stage is just a non-inverting amplifier. So I'm going to draw the differential half circuit. See, here we are concerned about the differential response. So we will draw the differential half circuit. That's a standard non-inverting amplifier. And for a non-inverting amplifier, if you guys recall from our previous discussions, we said the frequency response of a non-inverting amplifier will look like a first order system. The DC gain is given by 1 by beta. Okay, here we are calling it as beta 1. It's the first stage feedback factor. So beta 1 represents that. That's the DC gain. And the 3 dB bandwidth is given by omega u1 times beta 1. Omega u1 is the UGB of this op amp. So that times beta 1 will give the 3 dB bandwidth of the first stage. Okay, so remember, just to keep things in, so just to, I forgot to mention one important point is that the second stage, if you see, right, that offers a resistive load. Okay, it offers a resistive load of R3 or whatever. Okay, but since the op amps is an ideal op amp is a VCVS amplifier, this load will not impact your UGB. So that's our assumption we make here, which is valid, which is valid for these op amp architectures. So that's why I haven't included that, but in an actual design, depending on your op amp architecture, you may have to include that as well. But here, to simplify this, we are only considering the first stage, assuming that the load of the second stage doesn't impact its frequency response, which is true if you assumed your op amp to be a VCVS op amp, voltage controlled voltage source model based, op amp, which means its output resistance is very low. If you use that approximation, you can ignore the resistance from the second stage. So from this, the UGB, the 3 dB bandwidth of a non-inverting amplifier is simply given by omega u1 times beta 1. Okay, so now if I were to use this model where I have written this gain as a single pole response given by the closed loop gain as a single pole response with a gain G1 and a pole of omega 1. Omega 1 here is your 3 dB bandwidth given by omega u1 times beta 1. Okay, since beta 1 is nothing but the feedback factor, we saw this in the previous lectures as well, can be written as 1 by 1 plus 2 RF by R, that is 1 by the gain of the first stage. So the 3 dB bandwidth of the first stage is given by the op amp's UGB or op amp's unity gain frequency divided by G1. That's the 3 dB bandwidth of the first stage. For the second stage, it's a subtractor. Again, we have analyzed this circuit as well in the previous lectures. You can go through the, I think it's lecture 18. I'm not sure the number, 18A, B or C. You can go through that. In that lecture, we derived the 3 dB bandwidth of a subtractor. We showed that the 3 dB bandwidth of a subtractor is again given by omega u3, that is the UGB of this op amp, times the feedback factor of this subtractor. The feedback factor, beta, is given by R3 upon R3 plus R4, which can be written as 1 by 1 plus R4 by R3, which can be written as 1 by 1 plus G2. G2 is the second stage gain, which is given by R4 upon R3 is the value of G2. So the 3 dB bandwidth of the second stage is given by, which we are denoting it as omega 2, is given by omega u3, the UGB of the second stage, divided by 1 plus G2. So that's what I've shown here. as a frequency response. This is the first stage non-inverting amplifier's frequency response. G1 denotes 1 plus 2 RF by R, and G2 here denotes R4 by R3. And you guys can see here the 3 dB bandwidth is given by omega U1 by G1 and omega U3 by G2 plus 1. So if you guys recall from our previous lectures and even the beginning of this lecture, we said that most of the gain, I think we mentioned this in the previous lecture, most of the gain for a instrumentation amplifier comes from the first stage. So generally your G1 will be much greater than G2. Okay, because your G1 is much greater, your 3 dB bandwidth of the first stage can be much lower, especially when you are setting your gain to be very high, which means your feedback factor for the first stage becomes very small. Then the speed will be limited by the first stage. Therefore, your first stage op-amp's UGB has to be really high. So that will dictate your overall bandwidth of the system. So remember, I told whichever is the smaller of the two. If the first stage UGB is smaller, then that will dictate the overall UGB. Oh, sorry, the first stage 3 dB bandwidth is smaller, then that will dictate the overall system's 3 dB bandwidth. Okay. Second stage, generally G2 is smaller. So if you design it for a high omega U for the second stage, that will not limit your speed. The speed will many times be limited by the first stage itself, especially when you are programming the gain G1 to very high values. Okay, let's say you are changing it to 1000, then your UGB will be, let's assume the second stage gain is just 1, then the UGB of the second stage will be the 3 dB bandwidth of the second stage will be op-amp's UGB upon 2. This is assuming G2 equals to 1. Whereas if G1 is 1000, assuming all the stage, the overall gain happens to be 1000 and all the gain is coming from the first stage, it will be omega U1 by 1000. Okay, which can be much lower than the UGB of the second stage. So therefore, the first stage by design, when you are designing it, especially if you want programmable gain and you want to vary your gain, you would preferably want your UGB of the first stage to be much higher than the second stage's UGB. So that's it about the frequency response of instrumentation amplifiers. Okay, to summarize, we have discussed the basics of instrumentation amplifier, the construction of an instrumentation amplifier, how to arrive at the structure of an instrumentation amplifier. Then we saw data sheets of instrumentation amplifiers, some popularly available instrumentation amplifiers in the market. We looked at it. Very briefly, we spoke about applications of instrumentation amplifiers. They serve as differential amplifiers which can amplify weak differential signals in the presence of strong common mode noise. And then we spoke about in great detail about what does the CMRR of an instrumentation amplifier depend upon, what are the factors it depends upon, matching of the resistors, and then we also showed the gain error between the two op-amps in the first stage can also cause CMRR degradation. Okay, so that usually gives us the specification for the DC gains of the op-amps. Then finally we spoke about the frequency response of an instrumentation amplifier, and we said the frequency response is usually determined or dominated by the first stage UGB. Okay, so that's why the first stage UGB, by design, the circuit designers who are building the instrumentation amplifiers should ensure the first stage UGB is much higher than the second stage. Okay, especially when the gain is programmable and most of the gain is allotted to the first stage. And we saw even gain error, the gain error of a error in the gain. If you, let's say you are using this instrumentation amplifier in a high precision application where the gain matters, accurate gain matters. So if you need very high accuracy in the gain, then since most of the gain comes from the first stage, we saw that the first stage op-amps DC gains has to be much higher, okay, compared to the second stages. And all these, the frequency response has to be better for it, DC gains has to be better for the first stage. All this boils down to the simple fact that the feedback factor for the first stage is very low, or the DC gain for the first stage or the differential gain for the first stage happens to be much greater than the gain of the second stage in general. So this is all about instrumentation amplifier. I wanted to discuss in great detail because I didn't find any good references. Most textbooks don't talk about this. That was my intention. Okay, in case you have any doubts, just leave some comments. I'll when I find time, I'll respond back. Thank you.